Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss their key ideas in simple language. And in today's episode, we are going to discuss this paper on dual degeneracy in mixed integer programming. So this is an computational analysis of dual degeneracy. So it doesn't really propose a lot of new methods. It just proposes methods for how we can analyze the dual degeneracy in mixed integer programming. And also, like, it presents lots and lots of different statistics about how frequent the degeneracy is in mixed integer programming and how does it change with branching and all those things, right? So they also propose like a few methods for using the information that we gain from learning if the instance is degenerate, and we're going to see all of those things in today's episode. Okay, so let's start with discussing what is degeneracy, right? So if you remember your simplex table, right? So the way we solve linear programs, right? So we have our objective row over here, and we have some basic variables. Let's say x1, x2, and x3. These are, let's say, my basic variables. You can have more, but let's deal with 3 for now. And here we store the objective coefficients for this variable, all the variables, right? So the x1, x2, and x3, right? So these are the ones which take non-zero values. All the other variables are at 0, right? So and these are my basic variables, and for them the objective coefficients over in my simplex tables is always 0. And the other variables, let's say x4 and other variables, these are my non-basic variables, and they can have 3 types of objective coefficients, right? So they can have positive, negative, or 0, right? So all of these objective coefficients, basically they are called reduced cost for so and so variable, right? So for basic variables, the reduced cost is always 0. For non-basic, it can be anything, right? Positive, negative, or 0, right? So positive ones, like, so this is the one where we decide when we are minimizing, if all of them are positive, then we have reached the optimal table. Positive or rather non-negative, right? So when we have negative reduced cost, then we can make that variable as an entering variable, and we can move that one to the basic variable and take one of this basic variable out of the basis and move it here, right? And we then keep solving our linear program. Now there are 2 things that can happen, right? So these ones are all of them. So first of all, right, so all of these variables are taking the value 0, right? Or in other words, like, so when we are dealing with practical linear programs, right, so in that sense we can say that these variables are at their bound, right? So they don't really need to be taking value 0, because typically we don't really adjust our linear program so that all variables are actually greater or equal to 0. We just keep them at their bounds, right? And so similarly, this variable may not be at bound. So in our case, we say that they are non-zero, but that's really the case, that they may not be at their bound, but some of them can still be at their bound, right? So for example, let's say this one is at the bound, so then we can say that this table has some degeneracy, and this particular type of degeneracy, it's called primal degeneracy. Okay, so the idea is that we can actually take this variable out of the basis and put some other variable in the basis for that, and that will not affect anything, right? So it will have same primal solution, and it will have obviously same objective. And on the other side, we have also another type of degeneracy, which is over here, right? So we have this x4 sometimes. So positive and negative are kind of we know what to do, right? So positive, we don't need to do anything. Negative, we can enter this variable into basis, but we can also enter this variable into basis when the reduced cost is 0, actually 0, right? So this one is called dual degeneracy, right? So when this one enters the basis, something will have to go out. And let's say, so if this is the variable that is going out, which is also kind of responsible for this primal degeneracy, then really not really much is going to change. But let's say some other variable will have to go out for this entering variable, which is not responsible for this primal degeneracy, right? So in that case, we can have a different primal solution, and it will still have the same objective. So that's why it is called the degeneracy, right? So the reduced cost is 0. So regardless of how we increase or decrease this variable, it's not really going to change the objective. So yeah, I mean, it is still going to be the same objective, but it will have a different primal solution. So some variables that were at their bound, some variables that were not at the bound will be now at the bound, and the other ones which were at the bound, for particularly this one, which was at the bound, may be taking a value that is not at the bound, right? The objective value still will be the same. That's why it says degeneracy. It is not really helping us with achieving better objectives. And so in this particular video, we'll be talking about dual degeneracy. So these are the one that is more interesting for our case. Okay, so first of all, why do we really need to worry about degeneracy, right? So for linear programs, it basically simply doesn't matter. They're still the optimal solution, same objective, so it doesn't matter what solution we get. And apparently, I mean, we don't really need to care about if degeneracy. If all we are doing is just solving LP, right? But most of the time, we are not really solving LP. We are solving MILPs, mixed integer linear programs, or maybe sometimes we are doing column generation or those kind of things where this kind of, it really matters, this degeneracy issue really matters, right? So a lot of times they result in something called performance variability, right? So we have multiple optimal solutions and we don't know which one the solver will return, and depending on which optimal solution the solver returns, we may branch differently or do something else differently, right? So we can have different cuts, or a lot of things can be done differently depending on which particular solution the LP solver returned, right? So there it actually matters. So and that basically results in this performance variability, right? Because sometimes some of these LPs will return different solution. Okay, so first of all, how do we avoid this degeneracy? It is very simple. It's called lexicographical pivoting rule that basically simply avoids degeneracy, and this is like not used in practice, right? So it is not very practical. It is kind of sometimes very slow, so people don't really use it. Okay, so for MILPs, like what can we do about this, right? So can we take into account this multiple optimal solution, right? So how do we do that, right? So that we are going to see that, but why do we need to do that? What exactly can we get out of it if we take into account all these different optimal solutions, right? So first of all, we can basically have more integral solution. So what do I mean by that? It's basically like some variables are fractional, right? So but let's say we looked into some of the other degenerate solutions and found that in one of them most of the variables are integer and only few of them are not integer, then that we can pick that one, and so that is like more integral solution. So we'll have to branch less and do a lot of less heavy lifting, right? So that's one advantage. The other advantage, like we can have better branching candidates. So how exactly we can have better branching candidates, right? So there are, as I said, like some variables we are talking about dual degeneracy, right? So those variables can take different values in different solutions, but the overall objective is the same. Okay, so let's say that there is one variable which is fractional in one of those LP optimal solution, but it is not fractional, it is integral in one of the other LP solution, right? So in that case, we know that particular variable is not really a good candidate for branching, because maybe if we branch on it, and if that one gets that integer value in one of the branches, then in that branch it will not improve the LP objective at all, right? So it will basically will get to the same LP objective. It's just that the solution is different optimal solution for that same overall linear program, right? So that's in one branch we will not improve the LP objective, and so that one is not really a good candidate for branching. So we can basically filter out some of those candidates like that, right? And we can also do more reduced cost fixing. So this is actually a preprocessor reduced cost fixing. So I think I talked about it in my pre-solve series. If you haven't watched it, you can watch it. I'll just put a link somewhere in the description. And so this is another thing we can do is we can do more reduced cost fixing if we take advantage of multiple solutions, multiple optimal solutions. Right, so next we are going to talk about measures. So how do we measure degeneracy, right? So first simple measure in the literature is called degeneracy rate. So what is this? It's basically like how many number of total dual degenerate variables, dual degenerate non-basic variables divided by total number of non-basic variables. Right. So if you want percentage, just multiply this by 100. So this is your degeneracy rate. Right. So dual degeneracy is basically like when we have the reduced cost is 0. So we just need to count how many of these non-basic variables have 0 reduced cost, and what is the total number of non-basic variables, and yeah, just multiply that ratio by 100, and that's your degeneracy rate. Right. So if we try to plot this number, right, so they basically benchmarked, they basically analyzed a lot of instances in different MIP libs and Coral in that paper. So when they analyzed it, they found this kind of result, right? So we have this tall building over here, we have this tall building over here. So this is like 100% all of those variables are actually dual degenerate, versus here it is like something around 0%, 10, 90. So 90 to 10 was like one tall building, 0 to 10 was another tall building, and the other buildings, other bars basically were like somewhere in between, right? So something like that and that, and yeah. So there are basically like lots and lots of instances that are not at all degenerate, right? So they are basically here, or they are totally degenerate, right? So or they are here basically, right? So in between there are very few instances, but like the curve, the bars basically looked something like that. So that's like one piece of information, right? So we have a lot of instances for which degeneracy is an issue, right? For these instances, we are not really that much affected by it. But they also introduced one more measure that is called variable constraint ratio, right? So what is this? What is variable constraint ratio? So let's say if we want to first of all find out different degenerate solutions, so how do we do this? Is basically we can fix all variables with non-zero reduced cost in my optimal phase. Okay, so which variables have non-zero reduced cost? Like, so all the non-basic variables can have non-zero reduced cost, and we are going to fix all of them to whatever value they are taking, right? So whatever they're basically at their bound, and so we are going to fix them at whatever bounds they are at, right? So all the basic variables have zero reduced cost, so they are still free, and some of the other degenerate dual degenerate non-basic variables, these ones, they are also kind of left free, right? And so once we fix all these variables, so we are now fixed to the optimal phase, and now if we play around with the objective, we can just move around to different solutions in that optimal phase, right? So this is basically optimal phase of our linear program, right? So in this case, one way of analyzing this dual degeneracy is that we just count how many number of free variables left, right? So all of these free variables are degenerate variables, dual degenerate variables, plus some of these are basic variables which have also non-zero reduced cost, right? And so we divide it by total number of constraints. So variable constraint, right? So this is the ratio that we compute, and this ratio is always greater or equal to 1, because for every constraint we have at least one basic variable, and that basic variable is free because it has zero reduced cost. Okay, so if we plot that one, then this graph looks something like that, right? So for different instances, so most of the instances it was like around 1, 1, 1, 1. So it was slightly increasing, and then suddenly it was like this, a big jump, right? So this was on a logarithmic scale, right? So this is like 1, 2, 3, and so till here it was like reasonable level of degeneracy, but after that it is like some of them were like even bigger than 100, right? So this ratio was bigger than 100. So yeah, it's a big ratios, right? So this is another measure of degeneracy which we'll be using throughout this paper. Okay, so let's say we have some basic variable, right? So that can take fractional value, and so let's say that this basic variable, it can be thrown out of the basic, can be pivoted out. So if it is pivoted out, then it will move to one of its bound, right? So in that case, the bounds will be integral. So this variable will be integral, and so therefore, if it can be pivoted out by some degenerate dual degenerate variable, then it is a bad branching candidate, right? So why do we care about this variable constraint ratio is that when we talk about high variable constraint ratio, right, so that basically increases the probability of that particular basic variable being pivoted out, right? So this is high probability. What we saw so far was basically the degeneracy levels at the root node, right? So when we solved the root node and we saw those two plots, right? So two tall buildings at the end and the curve which looked like an exponential curve. I mean, not really exponential, but that kind of shape. So all of that was happening at the root node, right? So now the question is, how about when we start branching, right? Does that affect degeneracy? So branching to degeneracy. So what is the relation? So does it increase? Does it decrease? Or does it stay the same? Or what? So that's what they basically analyze next. So it's basically they started branching on those instances, and for every depth level, they started measuring the degeneracy, both the measures, like so the rate and the variable constraint ratio, and it turns out that about 50% of these instances, total all the instances, they basically don't change degeneracy much, right? So don't change. Okay, so or rather they change it by like very little, right? So up to 1 to 2% or something like that, and so it's like if they were highly degenerate at the root node, they remain roughly the same. If they are not highly degenerate, then they remain not degenerate, right? So very little changes for about 50% of the instances across different depths. So they analyze up to 20 depth level, right? So for about a lot of instances, over 300 of them reached that depth level, and for them that's kind of a reasonable number for analyzing, right? But on the other hand, we also have about 25% of instances that change degeneracy by more than 10%, right? So there's ones which are like not super degenerate are now degenerate, and the ones that were degenerate before are not degenerate, right? So overall, even at the root node, like so 87.5%, that's the number they reported, they are somewhat affected by degeneracy at root, right? So they experience degeneracy at root. So this is a big number, right? So 87.5, almost all instances have some sort of degenerate variables at the root node, and a lot of this degeneracy, 25%, is like not something that we can ignore. So that is basically changing across the different depth level, right? So when we start branching, the problem becomes different, and then some of them become degenerate, some of them reduce their degeneracy, and all those things happen. Okay. So this was about degeneracy rate, right? So what about this variable constraint ratio? So this apparently we see ratio. So this they basically saw that it is decreasing with depth, right? So decreases at higher depth. So initial, like, so overall they're still degenerate, but overall this measure of degeneracy, it is kind of decreasing. So yeah, that's the way things are, because like probably more variables are fixed or something like that, but I don't know why. So there's something is happening. So this one is, so change is basically happening in both direction. Okay, so it is like increasing as well as decreasing, and roughly like the percentages are same, like so some instances increase degeneracy, some instances decrease, and that spread is roughly same, but whereas this measure apparently says that at higher depths it is decreasing. Okay, so we have dual degeneracy, which is changing all the time with branching, and so variables can take different value. Variables can take different values. Right, so let's try to analyze this thing, right? So variables taking different values. So let's say that we construct this interval where this is like the lowest value that this variable can take, and this is like the highest value that this variable can take across all the different dual degenerate optimal solutions. Okay, and so this is called cloud interval. Okay, so sorry about this little clouds appearing here and there because I'm learning video editing. So for now it is a bit annoying, but eventually when I finish learning all this video editing part, so the quality of these videos will improve. So bear with me till then. Okay. Okay, so let's get back to the topic and let's see how do we analyze this one. So if this can be, let's say we can ask multiple questions about this cloud interval, right? So what about this cloud interval being empty? So for how many of these variables this cloud interval is empty? So if it is empty, that means basically that particular variable that is taking the same low and high values and in all different solution, right? So it is basically fixed essentially, right? So we don't really need to worry about that particular variable. So is it empty, or how many variables are taking how many variables this cloud interval is empty? So that's one thing we can analyze. And the other thing we can analyze is if it is not empty, then does it contain integer, right? So if it contains an integer value, that means that it is possible that in some optimal solution this variable will take an integral value, and therefore it might not be a good candidate for branching, right? So these are the two records that we can use and that can potentially help us with branching, right? So technically, how do we generate this kind of cloud interval? So a trivial way that is mentioned in the paper is simply just that it basically involves solving a bunch of auxiliary LPs, right? So how many? It is basically 2m plus n auxiliary LPs. So what is m? M is the number of constraints. What is n? N is the number of dual degenerate variables which are non-basic, right? So for every basic variables, so first of all, how do we generate this? I think I already mentioned this earlier, that we fix all the variables that are that have basically non-zero dual cost, right? So when we have non-zero dual cost, we fix all of them. So we are now reduced to the optimal phase. And then what we do is we remove the original objective, and then we say that, you know what, I want to analyze this particular variable x phi. So let's maximize this x phi and keep everything else. So this variables are free, right? So this variable m plus n variables for free, the basic variables for free, and the other variables for free. And so for x phi, I can get the value for high if we maximize that x phi, and if we minimize, I can get value for low. So for basic variables, I have two directions, maximize or minimize. For the non-basic variables, they are already at their one of the bound. So we only have one direction. Either we maximize it or we minimize it, right? So for that, we don't have this coefficient 2. So all of these auxiliary LPs we can solve, and we can get all of this interval, but that's like super expensive. So people don't actually do that. So what people actually do, that is something that is mentioned in a different paper, which we will study in a different episode. So we'll not study how to generate all of this in this episode at least. Okay. So let's try to analyze these two questions, right? So how many are empty and how many of them contain integer variable values and all those things. So let's say if we have a variable constraint ratio which is greater than 2.0, then it turns out that not a lot of them are empty, right? So most of them are they have like basically non-trivial cloud interval, right? So at the root node, let's say, it turns out that about 25% of them, they have all of the variables, all variables that have all vars that have non-trivial cloud interval, right? And it turns out about say 8% instances were there where none of the variables had this kind of trivial cloud interval, right? So this is basically 0% vars had non-trivial cloud interval, right? So there are lots of basic like metrics about that. So they maintained they basically described all these different statistics about what percentage of variables are they have non-trivial cloud integer, and how many instances have that many variable, right? So about 50% of them, let's say, had 80% variables which had non-trivial cloud interval, right? So this is happening at the root node. And what about at higher depth, so depth 20, right? So it turns out that this kind of things basically roughly the same, but these two extremes, they basically reduce, right? So this 25% for all variables, that reduce that number to 5%, and this 8% number where none of these variables had non-trivial cloud interval, right? So all of the variables had trivial cloud intervals, so that number reduced to 3%, right? So the extreme cases basically dropped. And I'm not sure why that happened, but my idea, like, so they didn't really mention this part in the paper. This is my opinion. So this is basically because there are more samples at higher depth, right? So because we have more samples, these extreme events kind of become less frequent, and that's my idea, that one of the reason could be that just because it has more samples, that's why this numbers decrease. But otherwise, I mean, this is something still interesting to analyze, right? So about this part, right? So when we think about bad branching candidates, right? So the ones that are bad branching candidates are basically these ones, right? So the ones that have integer values in their cloud interval, and they basically observe like similar statistics for this root and the depth 20 levels, right? So had like very high extreme values, but then those numbers basically reduce at the higher depths. But yeah, so that's the thing. So the branching, so we have lots and lots of bad branching candidates at the root node, whereas at higher depths we have fewer. I mean, so they're still high, I mean, so this extreme value is low, but then they're still, if you consider the variables which had non-trivial cloud interval, 80% of the variables that had non-trivial cloud interval, those numbers were still high, right? So that was not super decreased, but yeah, so the extremes were decreased, and this was like my analysis of my probable reason of what could have happened. Okay, so we still have lots and lots of bad branching variables occurring all the time. Okay, so let's quickly summarize what all things we saw, right? So we talked about dual degeneracy. So first of all, if we didn't know about different types of degeneracy, we have primal and dual degeneracy, and the dual one is the one that is kind of more interesting for MILPs and other stuff, right? So dual degeneracy is something that we saw. What is that, and how that affects the MILPs, right? So how we can take advantage of dual degeneracy. Particularly, we also saw that lots and lots of instances, right? So about 87.5%, that the number, that is like very huge number. Those many instances in like Maple benchmarks, different Maple benchmarks, right? They have some level of dual degeneracy in the root node, right? So that's a very big number. And yeah, of course, that basically says that we need to worry about it. And it's not just that we should worry about it at the root node. We need to worry about it at every branching level, right? So it basically changes a lot with branching, right? So we also saw how we can basically take advantage of this information of dual degeneracy, which is called cloud interval. We can compute this cloud interval, and we can basically, using that, we can filter out some variables, right? So all of those things we saw in today's video. And yeah, so that's pretty much it. So hope to see you in the next video. If you haven't subscribed already, please do subscribe. It really helps me out. So I will see you in the next episode. Bye.